There we go. Um, so, so this talk is about compaction with Spark. It gets pretty technical, but it is meant both for people who do not know much about compaction and wants to learn when to use that, to use it, why, and what are some of the challenges that may be associated with it. But it could also be for people who already kind of dabble in it and want to get actual practical tips for improving it. And that gets even more technical, so there's a bit of both. I'm Gilad. I started in semiconductors, actually. My background is in chip design. My first startup was in chip design. That got acquired by Synopsys after a few years. And then after 2 more years in Synopsys, I started DualBird, which is in the big data infrastructure domain. What is DualBird? So we are in stealth. Thank you for asking. And no, but actually this slide is outdated a bit. As of last week, we launched our website. No PR yet, so we're kind of transitioning out of stealth. So I did just this morning add another slide that does explain what DualBird does. So if you're curious, stay tuned at the end. Compaction. So compaction refers to the very common practice of taking a lot of small files, and at the end of that process, in the output, you'd get much larger files. And the reason why we would want to do that is because it improves querying time of the same data very significantly. So that ultimately, more generally, compaction could refer to any maintenance operation that would improve the querying time on that data, and not necessarily just taking a lot of small files and making them large files. So you could sort, you could do disk partitioning, bucketing, vacuuming of delete files, for example. And this is becoming increasingly more and more adopted, especially with open table formats like Apache Iceberg. And so that's why I'm here to talk about it. As I said, with this extremely scientific graph, you can see that doing compaction is much better than not doing compaction for the querying time, and adding sort on top of that would usually get you an even much better result. Just one word about how much compaction we want to do when we are talking about the size of files, parquet files, row group sizes. I would go with at least these numbers. These are the defaults in Iceberg. I don't know if you guys are using Iceberg, but if not, use at least these numbers. The reason why I'm saying at least for half a gigabyte for parquet files and 128 megabytes for row group sizes is because you could actually need, and that's a mistake a lot of people make, you actually might need much larger row groups. Think if you have 100 columns in your table, I'm sure some of you have much more than that. Each column on average would be 1 megabyte if your row group is 128 megabytes. So each column would be 1 megabyte on average. And when you go to access that from, let's say, your data lake, your AWS S3, that access size would be 1 megabyte. That is very far from what is optimal for an S3 access. You'd want to make much larger accesses. So in many cases, that's actually not enough. So definitely don't do less than that. You might want to do more. Okay, few more tips. Don't want to spend too much time on this. If anybody wants, I can send you the slides later. There's a bunch of other configurations that you should also be changing as you compact. Otherwise, you might lose a lot of the advantages of why you compacted in the first place. So for example, if you don't change this, you might end up with a lot of empty partition if the row group size is actually bigger than that configuration, which by default is also 128 megabytes. If you don't change that, you might be blocked on smaller S3 accesses, even if you can do larger accesses. Yeah, there's more tips. I'll send it later to anybody who wants. Okay, I do want to talk about, well, compaction of just making larger files. Bin pack compaction, as it often called, is pretty common, pretty adopted. Not many people do, not enough in my opinion, do sort-based compaction. So I am going to talk about that for a bit. I'll explain why it's good to do sort-based compaction. Actually, let's start by explaining why some of the misconceptions around it, because we are not actually doing sort-based compactions to improve join performance, group by performance. This is a common misconception. It is true that sorted data, if your query compiler knows that the data is sorted, it can do joins or group bys much more efficiently. But that's not what happens when you do sort-based compaction, because it's not an actual global sort of your entire table. It's a semi-global sort. I'll explain that in the next slide. Another reason, which is not the reason why we do sort during compaction, is to improve compression ratio. It's true, if you sort your data, compression ratio does improve. It could be negligible with high numbers of columns, unless you have really good correlation between your columns and your and the keys that you're using to sort. You're not going to get much compression ratio out of that. The reason why we want to do it is actually for filters. So if you know what kind of queries you're going to do on your data, if you know that 20% of your queries are going to be filtering according to some field and maybe other 15% on some other field, it would make a lot of sense to do sort-based compaction where you sort according to these two fields. The reason for that is that when you sort, you get really good high-quality statistics for minimum and maximum in your Parquet files, in your Parquet row groups, if you have Iceberg on your metadata. And that way, whatever query engine you use for querying can prune out a lot of files and row groups and just read much less data in the query. And that improves your query performance very significantly. So this is why we sort. Like I said, it is global sorting or semi-global sorting, which means that you group some of your table together. You don't necessarily sort the entire table together, but rather you create subgroups in the table and do global sort within them. In case of Iceberg, the default is 100 gigabytes of compressed files. It could be different numbers, but it is still global sort in the sense that you sort outside of a single Spark partition boundary. And that's a big deal because it means that it involves a shuffle. That's the difference between just sorting within a partition. It means that you actually sort data that doesn't fit in your memory. So given that, I'm going to explain a bit on the internal side here, how it works, what the algorithm is for sorting data that doesn't actually fit in your memory. So there's two main algorithms for that. First one is external sort. That's the algorithm used by databases since the 70s for sorting data that doesn't fit in memory. Essentially, you take small pieces of data that do fit in your memory, you sort them internally, and then you write them to the disk sorted. Then you start, as all the data is written to disk in small sorted lists, you start reading them from disk and merging them into longer sorted lists. You do that iteratively in a merge tree until finally you have one long sorted list. Other than the obvious downside of this approach, which is you read and write the data, send data multiple times to disk, there is another big problem here is that it does not parallelize well. As you get to the lower layers in the tree, you don't get good parallelism. If you have a big Spark cluster and you try to do that, you're going to end up with many underutilized resources. There's a different algorithm that solves the parallelism issue, which is to do range repartitioning. So you take all your data, you partition it according to non-overlapping ranges, saying all the smallest data goes here, all the biggest data goes there, and then each of these ranges would hopefully fit into memory. And so then you pick up the ranges, the data that is divided into ranges one by one, and sort each range internally. The problem with that algorithm is data skews. So there's no guarantee that the ranges would be, the data in the ranges would have the same size. And you could end up with partitions that are much larger than some of the other partitions, to the point where you even get back to the original problem that you have of sorting data that doesn't fit in memory. So what Spark does is combines its two algorithms in the sense that it starts with doing the range repartitioning, but inside each partition, it would do external sort if the data has to spill to disk, if it's too big. So it gets the best of both worlds. Okay, that's enough about general sorting. Now that we kind of understand the concept, I'll explain the different building blocks and what actually happens during a compaction flow inside Spark when you try to sort. So you start by reading the data from disk, doing decompression, Parquet decoding, and because Parquet is columnar, but Spark operator's implementation is row-based, you have to do column to row, which is another operation. Now, finally, you're ready to do what you were set out to do, which is to start dividing the data to ranges, to do target selection. So for each row, we calculate which range it belongs to, and then we write what is referred to in Spark as shuffle files. So you do shuffle right, and compress them so that at the other side of the shuffle, you can read them, and now they will be partitioned in the way that you wanted them to be partitioned. In this case, in ranges that you can sort. So now we're doing finally the actual sorting of each of these ranges, going back to row to column, Parquet encoding, and writing the files back to disk, compressing them. Is that all? Well, those of you on the more perceptive side of things would notice that I left this empty, so no, it's not all. Gets even a bit more complicated than that. Let's talk about shuffle for a second. So those of you who are familiar with how Spark operates would think about probably hash shuffle. When you think of a shuffle, when you do joins, when you do group bys, when you do window functions, Spark would use a hash-based shuffle, which means that you take a hash function and you use this on the keys of the shuffle for each row to calculate the target for that row, where that row should end up after the shuffle. In case of a global sort, this is not enough. As I explained before, we want to do range-based shuffle. You want to understand which range a row belongs to. So unlike a hash shuffle, you have to actually determine what those ranges should be. So how does Spark determine what the different ranges should be? It does another job, which is a prerequisite of the other job, just to determine these ranges. So what Spark does here is insanely inefficient. It reads the entire data, does decompression, decoding, column to row, only to sample very few rows out of that data. Each executor would send these rows to the Spark driver, where the driver would determine the ranges for the global sort. Only then the actual job can begin from new. This is so inefficient. All that Spark had to do here to make this much, much, much better is to just read here only the fields that are actually needed for the sort, only the sort keys. But Spark actually reads the entire data here. So in this kind of job, just the global sort, Spark would read all the data twice. I looked at the code. It's tricky to solve, but it's doable. We might contribute that in the future to the open source. We'll see. By the way, there's also a chance of a resampling job. I'm not going to get into that right now. But anyway, to try and understand how significant this is, you can see in this breakdown that this sample portion can take anything from 10% of 25% of the entire job. So it is pretty significant. This slide shows the breakdown of the different stages. I did distinguish here between the case where you have spills on the read side and the case that you have no spills on the read side. Because in compaction job, it can happen in any Spark job, definitely any ETLs, but especially in compaction, it gets pretty common to have spills on the read side. And as you can see, it can make the read side much longer. So given that it's so significant, let's talk about that for a second. Those of you who zoned out during the explanation about Spark internals and sort might want to tune back in now, because now it gets practical again. Disk spills. In the compaction job, the reason why you would get this is, as always, large data skews can lead to disk spills. Badly tuned system, and I'm going to talk about that for a second, because some of this can be mitigated. And in some cases, it's just that the target for compaction is too high that Spark has to spill. And this is a problem that's harder to solve because by definition, you want large partitions if you want to write large files. This is also why the tools to try and fix disk spills in compaction context are not the same as the ones you use for any other Spark job or ETL. The problem with compaction and why you can't, in other cases, you would, for example, increase the number of partitions, thus making each partition smaller and decreasing the chances of a spill. In compaction, again, by definition, you might not be able to do that, because if you decrease the partition size, the files in the output would be smaller, which negate the entire point of why you're doing compaction in the first place. So what can we do? There were a few people here before me talking about debugging Spark with UI, so this is definitely not the best way to do it. This is Spark's web UI. I definitely recommend you upgrading to DataFlint if you're doing that. But anyway, this is Spark web UI. It can show you the minimum, median, and maximum of disk spill that you get in your partitions. So you can look at that, and specifically on the sort operation, that is the one that is most likely to spill. The sort operation that is after the shuffle, you can look at that and see if your minimum partition is non-zero, meaning that even your smallest partition spills, it means that you just don't have nearly enough memory per core to avoid spilling. In that case, your options might be to either decrease your compaction target, which you might not want to do because you wanted larger files. Another option might be, if you haven't done that yet, to choose a cloud instance with higher ratio of memory per core. That could help fix the problem. These instances are more expensive per hour, but in most of these cases, the cost you save by removing the spills would be larger than how much more it costs per hour. So that is something that could resolve that issue. But very commonly, you'd actually see that the minimum partition doesn't spill, it's 0, and the median partition does spill. That means that more than half of your partitions spill, but many of them might not. In that case, what might really work is just reducing the number of cores in your executor. So if you have an executor with 8 cores, try to reduce that to 6 or 7. That could actually remove the spilling. Each core would get more memory, a little more memory, and that could remove the spilling. You do lose some of the parallelism, but in these cases, it is usually worth it and makes the job actually finish faster. Okay, how are we with time?
Yeah, you have like 5 minutes.
Awesome. Okay, so to talk about something even less important, this is just me venting about Spark sort not being stable because there's just absolutely no legitimate reason for why that is. Sort is not stable. Unlike most of the other libraries, it doesn't even offer a stable version, even with lower performance. It does have impact, actual practical impact, because it means that the query compiler in Spark cannot assume stable sort, which means that data in some cases might have to be resorted, even that was already sorted on some dimension. And it gets even more annoying during testing because you can't count on the determinism that stable sort gets you. I would concede that in a distributed context, When you have global sort, it is harder to maintain stability. It requires some management. It is doable, but I'm not even talking about that. Spark sort is not even stable when it tries to sort within a single partition, and that kind of annoys me a lot. And I'll explain why that happened and who's to blame. Well, it's actually not that guy, is okay. So Spark does a few different things when it comes to sort data inside a partition. It uses team sort when the keys are longer than 8 bytes. So team sort is a stable algorithm. So that's not the problem. In the photo is Tim Peters, who is the inventor of team sort. You heard me correctly. It's called team sort, and the guy's name is Tim. Next is radix sort. So in 8 bytes keys or shorter, Spark would use radix sort because it's faster when the keys are short. But radix sort is also a stable algorithm. Okay, in the picture, Herman Hollerith, the inventor of radix sort. Okay, so I'll get to the point. Specifically, when some of the keys are null, Spark would move all the null keys to be first because it does not want to apply radix sort to the null keys. The way that Spark would implement that is they would take these null keys and move them to whatever key was first, swapping the location, so it moves the key that was first to whatever location the null key was in. So it then it starts radix sort, all the nulls are first, it maintains the correctness of the sort, but stability is lost. And that is just nonsense, because I already fixed that internally. That's one of the first contributions we're going to do in open source Spark whenever we get the time to start doing contributions. Yeah, in the picture is Sir Tony Hoare, the inventor of the null reference. And by the way, also quicksort. So in conclusion, you want to do compaction if you don't do that already. Even better, do sort-based compaction. And disk spills are manageable. You just have to know what you're doing in the compaction. Again, if you want, I can send you these slides later. And yeah, that's it. Oh, as I promised, I did add a slide this morning about DualBird. So what we do in DualBird is, I did mention before, my background is in semiconductors. So in DualBird, we leverage FPGA instances that are on the cloud already. FPGAs are chips that can let you burn your hardware into them, meaning that it's reconfigurable hardware. So I can develop hardware, the same hardware that I would develop to tape out chips, silicon chips. I can just burn that into an FPGA that is already on the cloud. That means, and that's what we're doing in DualBird, is that we can provide hardware, custom hardware level acceleration, but deliver it as cloud software. So for a Spark user or an Amazon EMR user, it's basically a Spark plugin that you download. You change the instance type. It's just a regular EC2 instance. You can reserve it or use it on demand or use spot instances. It's just a regular EC2 instance. So you change the instance type and you get the acceleration out of the box. But because it is custom hardware, it is hardware specifically developed for big data processing, you get very significant acceleration. So it's 10x to 100x performance improvement and 50% to 90% cost reduction. And to add on top of that, it very significantly reduces the data engineering work around the maintenance and creation of ETLs or other Spark jobs. So there are just much less knobs to play with. If you ever want, I can gladly explain why. We completely eliminate many of the problems I discussed in this talk, like disk spills and data skews, virtually non-existent with our technology in all but the most pathological use cases. Oh, and there is a benchmark here specifically on sort-based iceberg compaction. that can show you that for any performance that you're trying to get, meaning any cluster size that you choose with either our solution or the CPU-based solutions, we very significantly outperform in terms of cost. Definitely vanilla Spark, open source Spark, but also the most high-end columnar C++ or Rust accelerators for Spark. Yeah, basically that is DualBird. So thank you, everyone. Thanks.